So thanks everyone for coming today. We are having week 6 of Introduction to Astronomy Research this week, and we'll be talking about fitting radial velocities with the radvel routine. We'll have a discussion about graduate school applications, tips and tricks for that. And then we'll have a discussion of the recent SETI paper, the Breakthrough Listen Search for Intelligent Life Searching TESS Targets of Interest. And so without further ado, I will hand it over to Corey to begin the radial velocity fitting discussion.
Okay, awesome. Thank you, Howard. Okay, so hey, everybody. I'm going to be walking us through, as Howard said, the radial velocity method today, and specifically using the package radvel. So give me just a moment to share the appropriate screen. Okay, I think everyone should be able to see my radvel notebook that I have pulled up right here.
That's good.
Thanks. Additionally, I have some slides that I will share as well. So, let's just zoom in on this from the outside first. So I think that most people in the class should at least have a passing familiarity with a few of the exoplanet detection techniques, since you probably learned about them earlier in the class from the exoplanet discovery paper you had to read, and then a few other parts of the class probably put some emphasis on this. So I expect that to an extent, but I'm also going to give us a kind of broad run through of what the radial velocity method is, or RVs. Again, everybody should have access to this notebook that I have pulled up right now. This is in the GitHub, and this week's notebook for the radial for radvel and that sort of thing. I did not write it myself, but I updated it this time. I also want to point out that I'm going to be covering a couple of other topics. So aside from the RV technique, which is a big topic, so I won't have time to talk about everything that's associated with it, we're going to talk a little bit about periodograms, or at least I will mention them. And so I just want to point out that there are some links in this notebook. So there's a little more information about RVs here. There's also some information about periodograms if you're interested. And then finally, I doubt if I'm going to get to it in my actual talk today, but if you go through and actually do this notebook, you will find at the very end there are some things that have to do with Markov chain Monte Carlo methods, or MCMC as I'll probably be calling it. And so if you need any more information about any of those things, they're right here. So without further ado in that respect, first I'm going to open up with some slides about the radial velocity method. So I think everyone can see this. So first of all, what is it? It's a particular astronomical detection technique where we, and one of the most common used to find exoplanets. And as you can kind of see from this graphic, it is essentially measuring the wobble of a star. So Kepler's laws and Newton's laws of gravity basically tell us that when a planet orbits a star, they actually orbit around a center of mass. And if that center of mass is appreciably far from the center of the star, it'll kind of do some noticeable wobbling. And of course, the bigger planet we see that's orbiting this, the more prominent this sort of wobble is. Now, we don't observe it directly. What we do is we use a spectrograph and we look at the spectral lines. As probably a lot of you know, stars, elements, and, because stars are composed of elements, have these particular spectral features, these absorption lines in this case. And basically when the star wobbles, you see the position of these lines get shifted a little bit, as is kind of indicated here on the right. As a result, we can see a shift in the velocity of this star we're talking about the radial velocity directions. That means towards us and away from us. And basically we can get either a negative one when it's coming towards us, or positive when it's going away from us, though actually that convention is sometimes not always used. But that's what I'll talk about right now. So basically what happens is that we look at a star and we see, is it moving towards us, or is it moving away from us? And we calculate what its radial velocity is. And over time, we do this several times. We do this over a sort of baseline. And we can get an idea of what this star's motion is going to look like. So we take data points, oftentimes on different nights. And so first, I just kind of want to show you what radial velocity data sort of looks like. So this is kind of a screenshot of some data from a collaboration that I work on with Howard. And basically, this is a particularly interesting star that everybody's interested in that group. And as you can see, we have a bunch of data points arranged in a sort of way here. Now, if it wasn't obvious from the slide before, what is it? signature of a planet, a non-eccentric planet, will often be that of a sort of sine wave. And it probably doesn't take too much imagination to sort of pick one out from this data here, I feel like. You can see that maybe at the beginning it's not so clear what's going on, but as time goes on, you can actually see pretty distinctive features of like a sinusoidal wave, kind of a periodic signal here. And it's actually one of the reasons I chose this system, is because it's pretty clear from looking at this what's going on. That's not always going to be the case when we're doing RV analysis stuff, but sure, we found the star, we think it has exoplanets, and we look at it for night after night after night. You can see we've been looking at it for about 2 years almost when I took the screenshot. And yeah, we see some clear periodic behavior that suggests exoplanets might be here. Using some methods that I'll be showing you in just a little bit, we can then fit models to the data. And so the idea is that we kind of give it some information about the planets, or maybe some of our best guesses anyways, and we do some advanced stuff that's part of radvel. And the computer kind of fits what it thinks is the solution to this system. And the interesting thing about this one as well, one planet signal was pretty clear. You'll find that this is actually a multi-planet system. It has several planets, in fact, which you probably couldn't tell by eye. You could tell there was at least one, but multiple, probably harder to decide. And so what you'll see here is that despite this large kind of sine wave here, there's the little amplitude variations going on that indicate other planets. So this sort of modeling is done in radvel, and I will switch over to that in just 1 second, but really quick, I also just want to brush up on some terminology that have to do with orbits of planets around stars and radial velocities. Some of these are going to be somewhat important. So really quick, I just want to say that I think the kind of parameters of a planet's orbit when we're doing RV analysis can kind of be broken down into 5 parameters, 5 important ones, which are the orbital period, is indicated here. And this is basically just how often the signal recurs or repeats itself. The semi-amplitude, which is, kind of what it sounds like. It's how big the signal is, the amplitude of the signal. We also have this, there are these 2 parameters here, the time of conjunction and the time of periastron. Now, you only need one or the other for the most part when you're doing RV analysis. The time of conjunction I prefer to use usually because it's synonymous with transit time. And then the time of periastron is sometimes used for other reasons. Finally, you'll notice that this signal here on the right is not a perfect sinusoid because it has some eccentricity. There are actually 2 more parameters associated with the orbit of the planet. It's eccentricity, which is basically how much it deviates from being a circle. And then finally, the omega parameter, which kind of controls, it's associated with the eccentricity and controls basically where in the orbit the planet is eccentric. So on the left, we have the top-down view of the orbit, and you can see a few of these things I was just pointing out. So we have this inferior conjunction or time of conjunction when it's passing between us and Earth. We have this omega term here. We have the periapsis, and the circular thing kind of shows its period. Okay, so keep a few of these things about planetary orbits in mind when we switch over to this radvel tutorial. So scrolling down just a little bit, aside from this information I talked about earlier, I just want to quickly note about installation. This is hopefully straightforward for people to install. Pip install radvel should work in a command line. And it should also install various other associated packages that have to do with radvel. I confirmed, like I created a new Conda environment, and I was able to tell that I could run this entire notebook on my brand new environment. I just installed radvel and I installed Jupyter Notebook, and I was able to run this. So hopefully other people aren't having issues with that. But basically going through the notebook example, this first cell here is this import, and you'll notice that there's a few things that we're importing, and actually a lot of these will get automatically imported with radvel if you haven't already imported them yourself. So basically just run this like normal. But then what happens in this next cell is that we're actually going to be opening up some radial velocity data. Now, radvel, just due to the nature of the software, people are installing it for the first time. Everybody does it for the first time at some point. So it comes with some data in a radvel example data directory. And so when you pip install radvel, you should have RVs of this particular system. We're going to be dealing with K224, or this long epic phone number as well is also another name for this system. And this is a system with a known planet, and we're kind of just do a faux investigation into the exoplanetary nature of this system. I also want to point out that these to-do comments in this notebook, which basically just means I'm not going to do them now, but when you're doing it yourself, you should do them, and they can kind of help increase how much you're going to be getting out of this. So this is an example of what it looks like in a text file format. We have our times over here, we have the velocities, and then we have the error bars, which can be important when we're doing these sorts of fits as well. Now, a visual representation of the data. The next cell shows, first of all, the data, and then the data points with error bars. And I think you may immediately notice that unlike the system we were looking at in my slides, it is not really easy to discern the existence of a planet here or not. I mean, we know the answer here. There's actually 2 planets in the system, but looking at this, you really couldn't say. Pretty hard to do. And that's, fortunately, we have computers that can do the heavy lifting for us and can basically tell us when there's a planetary signal or when there isn't, and help us, solve things that our eyes by themselves cannot do. So I mentioned earlier that we would be using these periodograms. Again, this is a really brief introduction. If you want to learn more about them, it's a big topic. But basically what a periodogram does is it takes RV data like this up here, and this is kind of a representation of it on the left, and it breaks it down. It kind of fits a bunch of different sine waves at different frequencies to it. And it identifies which frequencies fit the data the best, which combination. So the result is what we kind of see here on the right, which is these distinctive peaks that correspond to a frequency that exists in the data. Now, planets always orbit with some frequency, which is why periodograms are very powerful tools for identifying planets, because we should see a periodic signal in the RVs if there's a planet there. Now, moving slightly more forward, so this should not require too much work on anybody's end if they're following along with their notebook or doing it on their own. But we create this periodogram, and here's the result of our periodogram on the data at first. Now, we're actually kind of restricting what window of frequencies you're looking at. And that's because you actually kind of get a lot of junk when you run periodograms and stuff. They're not perfect. A lot of times you'll get these spurious signals that just result from bad sampling, aliases, or it can be stellar activity, all sorts of different things. So, it's not as easy as just pointing a periodogram at it and getting a period, but to an extent, that is a lot of what it is. So we see a prominent signal right here, which is associated with what we actually happen to know is one of the planet's periods. So we're going to kind of turn our attention on this, and we're going to move forward. Like, we think there's a planet here. Let's use radvel to figure out what we can about the planet. So when you're doing radvel, you start off with initializing the model. First, we tell it that we're only looking for one planet, and down the line, we may do this with more planets. And then what we're going to do is define. I talked earlier about these kind of 5 important parameters of the orbit. And so you'll probably recognize 3 of them. So peer 1 here is the period. And so that's, again, how long it takes the planet to go around the star, right? So using the periodogram, we have an idea of what the planet's period is. This TC1 stands for the time of conjunction in this case. So again, a lot of times from some other sources, we just happen to know what that is. And so we here put an initial guess for what we think the time of conjunction is going to be. Another one you should recognize is this K, or the semi-amplitude. So that's basically how big do we think the signal is. Our initial guess right here is 3 meters per second. These 2 terms here are actually some kind of a reparametrization of the 2 eccentricity terms, but you don't need to focus too much on them for this tutorial. We're going to not let them be kind of a part of the model. What we're going to do is we're going to fix them at 0. The reason is when doing RV analysis, a lot of the times these eccentricity terms kind of cling to unphysical values, and they can kind of hinder your search for exoplanets. Now, eventually, when you have a lot more data, finding these eccentricity terms can be very important. But for now, we're going to keep them fixed because they tend to mess things up. Finally, we have these additional 2 terms here. These don't have to do with the planet's orbit, but they're kind of just, they are the trend and the curvature. So they kind of, you may have noticed in the data I showed you earlier that there was kind of a line that pointed straight up along with the fit. Sometimes these things happen in the data. They suggest the existence of perhaps additional planets or even a binary or something like that, depending on how big they are. So we're just putting some initial guesses for these, and we're going to let them float as well. And then our final free parameters in our radvel model are instrumental. Basically, we have this gamma high res because we're taking data from the high res instrument. And this is the offset, as it kind of says, the 0-point offset. And this is more important when you're dealing with multiple different instruments because they all have different little offsets, and you kind of need to be able to move them all up and down to basically use data from multiple instruments together. That's where it becomes most important. And then finally, we have this jitter term. This is basically a term that inflates the error bars to collect, say, variability we didn't catch, or it could even be additional planets or something like that. We let it kind of absorb a little bit of that sort of thing, but we don't want it to go too crazy. But most instruments will have a little bit of jitter. So after we've initialized our model and given it our initial guesses, we plot what it looks like. And frankly, it doesn't look very good, does it? Yellow line is not fitting it very well. And this is why we do what we call a maximum likelihood fit. So usually when you're doing this kind of analysis of RVs, you don't start with perfect guesses. So this maximum likelihood fit will basically take our parameters and vary them all a little bit using a sort of built-in optimization algorithms. So we have our initial values, and then, so notice that the period of say was originally 43 days, and after we optimize, it gets moved to 49. And then we print out our results, and the model seems to fit the data considerably better. So I call that a success. And now we print out an RV plot of what this sort of looks like. And this is a built-in radvel function, which is really nice. You can see our model that we had earlier. You can actually see that there's a little bit of curvature here that gets fit to the residuals. And then finally down here, you'll have a number of these equal to the number of planets you're fitting. So we were only doing one. So we see one, what we call a phase fold. You basically take all the data, subtract all the other planets, and you kind of organize them into a way that really accentuates the sinusoidal nature of a single planet. And it looks okay. I've seen better. Moving forward, what you typically do in this situation is you look at the residuals, and here's a plot of the residuals. This is basically the data minus our planet. And there's still a lot of variability here, more than 5 meters per second away from zero. So that tells us that maybe there's the existence of additional planets. It could also mean stellar activity or something like that. But we're going to go forward thinking there's another planet here. So now we run another periodogram, and we cling onto one of these other peaks, which we kind of happen to know is the right one as well. And we move forward with our analysis, except now we think there's 2 planets. And so we set the number of planets to 2. And I pointed out that these kind of 5 free parameters associated with these planets. Well, now we have a second planet floating around. And so we take different guesses for what its period is, for what its time of conjunction is, and what its amplitude is, because these are unrelated. They can be different. Once again, we're going to fix these eccentricities to 0, and we're going to fit everything else like we did before. These trend and curvatures are going to stay the same. Instrumental terms are going to stay the same for the most part. And then we do an initial fit to the data, and it looks kind of bad, just like last time. Maybe a little better, but it's not important because we're going to optimize this. And now we get a fit that looks a lot better. I would go as far as to say this looks pretty good. And so then we go forward, and we do print a little summary plot here. So you can see our 2-planet fit to the data here, curvature and the residuals like before. And now we have 2 phase-folded plots of the planets, planet B, planet C. And overall, I would say this looks a lot better than what it was doing before. And there's a lot of other cool stuff you can do with it. So as expected, we're not going to have time to go into this last part, but I highly encourage everybody to do this on their own. This Markov chain Monte Carlo stuff. This is typically what scientists are going to do after they fit the data using these optimization to really refine the parameters, get things like uncertainties on our fits, and explore other parts of parameter space. Yes, so I think we just hit 20 minutes, maybe just about. So I think that I will probably pass the baton off at this point in time. Hopefully people learned something about this RV fitting stuff. And yeah, Howard, take it away, I guess.
Thanks, Corey. That was just great. And so Corey's put together a tutorial here as well, and there'll be solutions posted next week. And so you guys can work on this on your own, try to get that installed and learn a little bit about how to fit radial velocity data. And of course, that's how Corey spends his days. So he knows all kinds of details that we didn't have time to cover. And so if you want to ask questions, you can do that on Piazza during the week. Thanks again, Corey.
Yeah, no problem. Happy to help with that too.
And next I'll hand off to Emily to start the discussion on grad school applications.
Hello.
I can hear you.
Ensure that everything is ready to go.
Take it away.
All right. Hello, everybody. Thank you so much for being here. Today, we are going to be talking about grad school applications. This is a process that is time-consuming and seems really daunting. So I'm hoping today I can at least clarify some points about it and make you feel a little bit more confident if you decide to take this route. For context, this is about graduate school applications in the context of physics, astronomy, and planetary science, or more generally, favored towards STEM fields. So if the departments that you decide to apply for are missing components or have extra components that I do not talk about today, that is why. These applications are also going to be in the context of universities within the US. So before you go ahead and dive right in, there are some things to consider in regards to should you pursue graduate school at all. It seems like the natural next step. You've spent 4 plus, maybe more or less 4 years getting your undergraduate degree. So it seems like, hey, now go on to graduate school. But that will ultimately depend on what your intended career path is. If the industry you want to go into only requires an undergraduate degree, you are under no circumstance required to go into grad school, and you can go ahead and pursue the job industry if you want, or you can go into education. If you decide to pursue graduate experience, that will open your doors to academia, teaching at a higher accredited institution, a university, community college, if you so decide. Or there are some research institutions that require a graduate degree in your specific field. So consider your options and consider your intended path before committing to a choice. Whew, excuse me, sorry. So you've decided to go ahead and apply to grad school. These are the basic general requirements. So you have your baseline, which is your GPA, your degree, and your transcripts. Every department will state usually a GPA limit, accepted undergraduate degree requirements, as well as transcripts, usually as close to your graduation date as possible. There are also examination requirements, which are the GRE, the TOEFL, and the IELTS. We'll get more into depth in there later, as well as required materials. These are your personal statement, your CV, and your letters of recommendation. So for your baseline requirements, we have your GPA and your transcripts. A GPA requirement is usually standard across all applications. A good GPA communicates a consistent academic performance and discipline, something that's really necessary for graduate school. If your GPA is below the threshold, but you still have time before you apply, you can work extra hard to boost it before your deadline. While a good GPA does not represent the entirety of a student, it is still considered in the application process. So if you don't have the confidence in your ability to be accepted on academic merit alone, experience in research, projects, or internships can help you a lot in that sense. In most cases, you need to be in good academic standing at your previous institution, no outstanding debts, no academic misconduct. Your undergraduate degree required by each department will often be the precursor to the graduate degree or in a very closely related field. For example, a PhD in physics will require a bachelor's in physics in most cases. Other degrees can be considered on a case-by-case basis, but that is not guaranteed. It will be up to the department. And finally, applying to graduate schools cost money. Application fees, transcript mailing fees, because a lot of them require them in physical paper, examination fees. Some of these can be waived or partially waived by special request forms if you qualify. So if you are in need of that kind of financial support, do not be afraid to reach out and ask for a fee waiver. Sometimes all you need to do is ask. It is an expensive process, and we want to be able to have all of you be able to apply. So if that is something that you need to do, go ahead and do it. All right, examinations. While not always required, certain graduate record examinations as well as other examinations, are requested through different departments. The graduate record examination is almost pretty much standard in recent years. Certain universities are no longer requiring them. So when you are cruising through and looking for departments and faculty and just doing your basic research on where you would like to end up, consider what tests you will need to take in order to qualify for their application. The general GRE is a math, quantitative, and analytical writing exam. It is available year-round on weekdays and weekends, excluding holidays. It is held in numerous locations throughout the country. You are able to take it pretty much at whatever time of year you need to. Due to the more selective nature of graduate schools, a specific score is not usually stated. So more or less, the better your score, the better it looks. Then there are subject GREs. I know that a lot of you come from many different backgrounds and are taking many different courses and are from many different majors. So the subject GRE may be required depending on the department. They are only offered 3 times a year, so make sure that you know if you need to take it or not. There are only 6 subject tests. There is biology, chemistry, English literature, math, physics, and psychology. I myself had to take the physics GRE to qualify for applying for physics PhD programs all around California. And it was a long overdue, expensive, but a really great learning experience and process. So know if you need to take it and be sure to get a slot for the next available testing date. So if you are from a country where English is not a primary language and you want to study at a US university that is where the courses are taught in English, you will usually be required to take a English literacy exam, a language proficiency exam. The most common one that I've seen is this top one, TOEFL. It is offered 50 times a year. And the IELTS is accepted in other countries, as well as within the United States in certain universities. The availability for that one will depend on the country of origin. For both tests, there are 4 sections: reading, writing, speaking, and listening. So always check with your local testing center or online for the country of origin to make sure that you can take this test on time. Your personal statement. This is the one chance to promote yourself beyond your academic merits. This will be entirely personalized for every department that you apply to. This is not going to be a copy-paste inspirational quote that you just send off everywhere. This is your chance to essentially not only sell yourself on your achievements, but sell yourself on your usefulness and your ability to fit in and do well in the program. So you're going to make each one unique to the program you are applying for. Word counts and requirements and prompts will differ for every department and for every program. So do your research. That is a very common theme for these, do your research. And I would like to reiterate, this is not about just your achievements. There are a lot of personal statement drafts that have come through, and it is just what you've done. While that's great, that is what your CV is for. This personal statement is more about what you could do. And with the guidance from these advisors and at this university, you can pursue this research and pursue your interests in this way. Yes, Alex, go ahead.
Yeah, I just wanted to add that the personal statement is also a great chance to address any shortcomings you think you might have in your own application. I know for me personally, my GPA was not great going into grad school, and that was because of a few bad semesters, and I was able to explain that in my personal statement. So don't leave people on the admissions committee guessing as to why you didn't get the grade that you could have gotten in this certain semester or some kind of example like that.
That is a very good point. I myself had to actually explain my GPA as well through my personal statement. That is a really good point. Beyond just being able to sell yourself and consider how you make yourself useful, it is to cover bases that cannot be covered from your other supplementary materials. So you need to consider this one of the most important pieces of your graduate school application. Your CV, we have already gone over this in previous weeks, focused on academic achievement and related experience. This is where you can list your internships, projects, specific applicable courses can be listed here. Not all programs will require a CV. That all depends on the department and the program, but one can be provided anyway. Sometimes there is a small section where you are allowed to post supplementary materials outside of their required materials list. And if you have a wonderfully fleshed out, impressive CV and you want them to see that and they don't ask for it, that is where you can just kind of file that in there for them to look at later. And also it always helps to just have a copy of it on your local computer or even just in print and keep it updated as best as possible when you complete related research or projects. Letters of recommendation. This is one of the, this is a time-consuming portion of it. You want to be able to get this addressed as soon as you know that you're going to apply for specific programs. Letters of recommendation are always required. They want to know that the person who is applying for this specific program is reliable and accountable and has a good reputation among people that they've worked with before. So you need to consider carefully who you ask. Always give them plenty of time to write these letters of recommendation before the deadline. Choose who you ask carefully, as these people will most likely be contacted and asked about their opinion of you and their experience with working with you. They take time to write, and chances are you are not the only person who has asked this person to write you a letter of recommendation. So certain persons will not be able to write you a letter if it would be a conflict of interest. For example, if the person who you want to be your advisor and you are at the same university with you as an undergrad and them as an advisor, they cannot write you a letter of recommendation for you to be their graduate student later on. That was the case with me. I had to lose the one person that would write me a very supportive letter of recommendation in favor of another professor. They are allowed to deny you a letter of recommendation for any reason. Just because you took their class or just because they worked with you does not necessarily mean that they are the best fit to give you the letter of recommendation that you need. So keep that in mind. Make a list of people, talk it out with them, send them an email, meet them in their office if that's what they prefer. You have to be very open and communicative so that these letters are written on time and submitted in the application when it's time. So a certain amount, if not all of these letters, have to be from faculty members. In the event that not all of them have to be faculty from your university, other good options can be supervisors from internships or work study, as well as supervisors from undergraduate research. They are people who know you in an academic environment and how you operate and how well you work. So, great references for graduate school. And finally, some extra tips and recommendations. Do your research. Absolutely do your research. There are cases where you just need to apply to the department and you will be assigned a PI later. There are also instances where you request a very specific person within the department. In order to do that, you need to know who is accepting graduate students. Are they active in research? Have they published anything recently? If so, where? Was it referee? You can find published research on Google Scholar or NASA's Astrophysics Data System, ADS, if you are going down the route of physics, astrophysics, planetary science, or astronomy. But that all depends on the department and who is working within it. If you want to know what it was like to work with this person, you can find previous graduate students of theirs and ask them. Usually those who were involved in research still have their emails plenty available. So never be afraid to reach out to them. But avoid being generic in emails. One of the best things to go your way is to be memorable. You want to be known as the person who cares and the person who is actively interested, right? Just dropping an email in their inbox where they receive maybe 50, 60 a day from other places because they're doing so many things at once. Just being like, hi, I go to this university and I'm interested in your program. Can you tell me more about what you do? that work is not enough. So if you actively put in the effort to research faculty, to research who is taking students, that will help you out a lot to make sure that you can name that person and they know you before you come to them. Before graduate school, if you want to make yourself feel like you're getting ready to be a little bit more useful, you can always develop some good skills. Coding experience is always helpful and always great. I think the three main languages that I've seen used are Python, R, and Fortran 77. Although that's a very particular case, I would highly recommend Python. As well as scientific writing. Sometimes one of the best ways to make yourself useful is to get yourself used to writing in a scientific format. It is much different than what they teach in undergraduate English courses. Sometimes specific courses are taught for scientific writing at all. So that's also very useful experience as well. Alex, do you have anything to add in terms of extra tips and tricks?
I think it would be good to get your personal statements read by as many people as possible.
Yes.
Being able to get multiple eyes on every one of your personal statements is really important, because I can't tell you how many times I have completely glossed over grammatical mistakes or something like that. And grammatical mistakes and like misspelled words, they can kind of break the flow of your personal statement and distract from the actual content of it. So it's really good to not have any, glaring mistakes in your personal statement. But also, if you can, if the people on the admissions committee at your own school, even if you're not applying to that school, it's good to ask, hey, can you read over my personal statement and give me any tips? Because they're the ones who are going to be reading this, they're going to be reading thousands of these personal statements. And sort of on the same note, make sure to make yourself stand out in the first paragraph at least. Like, I know a lot of people have all these awesome stories about how they loved astronomy, when they were young, and but everybody sort of has those stories. And so someone as valid as they are, someone on an admissions committee can kind of get tired of reading that. So try to find other ways to make your personal statement stand out from the first sentence.
That's absolutely right. Peer review is extremely important to make sure that fresh eyes can find mistakes that you are just continuously glossing over because maybe you've been staring at it for way too long. And exactly, when in doubt, always ask. And always ask the people that are doing this on a regular basis. They'll be able to provide you with really valuable advice on how to stand out and how to give yourself the best chance of being accepted. All right, that is all that we have for today. Thank you guys so much.
Thanks, Emily. Thanks, Alex. Does anyone else on the panel like to share any other tips before we move on to the next topic? It's a wide-ranging topic, and there's lots to discuss about it. People have lots of different personal experiences as well.
One kind of funny thing I wouldn't mind sharing. I mean, I'm not sure if this qualifies into some sort of advice, but it was an interesting thing I noticed in my grad school applications is that the professor that I spent a lot of time doing research with right around when I was applying was actually not one of the ones I got recommendations from. I got 2 recommendations from people I knew in my undergrad, because I took a year between grad school and undergrad and did research in the year. And the situation was weird. I was told by the guy I was doing research for that a lot of the schools I applied to reached out to him, even though he was not one of my letter writers, and asking like, why didn't you write him a letter? Did you have a falling out? Is there something weird between you? And so this is just something that I'd kind of found, like, fortunately for me, he reached out to me and he was like, that wasn't the case. And we had a conversation about it. But I would say that it's sometimes it can actually harm you if your letter writers, like who your letter writers are, say something, I think, about your backstory as well. So I think you want to keep that in mind. Just an interesting thing that happened to me.
Yeah, it's a good point, Corey. Thanks. There's one question I can answer while people have other comments they're thinking of on the panel, and that was if you're an astro major and you're thinking of moving into data science, That's really a natural fit. There's a lot of overlap in in thinking skills, critical thinking skills, plotting, data analysis type stuff that carries over really well from astronomy to data science. So I encourage you to stay in astrophysics and then maybe take some data science courses, but I think it's a really valid way to get from one to the other. If students have other questions that you'd like to ask the panel during the week, you can ask them on Piazza and we can get back to you. Almost everyone here has done some letter writing and some personal statement writing, and even in some cases some letter reading. And so there's lots of advice here for you if you'd like some more. Last chance on the panel. All right, so part 3 of week 6, I'm gonna hand it back to Corey for a discussion on the breakthrough list and search for intelligent life, searching for technosignatures and observations of TESS targets of interest. Take it away, Corey.
Yeah, thanks, Howard. Okay, let me get this into a screen sharing sort of position. Okay, so here we go. Yeah, as Howard said, so this week's paper is a focus on the breakthrough list and search for intelligent life. This is sort of a project inside of SETI, which is the search for extraterrestrial intelligence, that is particularly interested in focusing on technosignatures, I'm sorry. So, just kind of going into this, I think like many of you, this is actually not a field of astronomy that I'm very knowledgeable about. So, I actually read this a couple of times, and a few parts of it I found to be somewhat challenging. And so, but I think I've dissected it, somewhat accurately at this point. And let's just go through it. So I want to point out a few of my highlights, and I think the things that are most important for those of you who have also read this. So first of all, the introduction, I think, does a pretty good job of kind of establishing the state of the field of sort of SETI and the search for extraterrestrial intelligence, right? I mean, I think it goes without saying that in situ sampling, which is an important part of many fields of science, is very challenging. In astronomy. I don't think that's news to anybody because we can't actually go to these planets and measure stuff. And so they basically, and I think in a clear way, break down that we really have two options then. If we're not going to go to these planets and look for life, we're going to have to either look for biosignatures or technosignatures. And they then go into a little bit of information about which one might be the more attractive option. And while scientists are looking for both, Breakthrough Listen is a project that is designed to search for technosignatures in this sense. And they talk about a few of the advantages that I've kind of highlighted here, basically, which is basically that searching for biosignatures is oftentimes difficult to unequivocally determine if they're actually from living organisms or if they're from some inorganic process. I mean, look no further than the recent Venus phosphine sort of debates where people are not sure if that's essentially thought to be a biosignature, but we're, still an open scientific question there. And that's kind of why they're making a case for why the technosignature search is advantageous. So next up, we delve into the Breakthrough Listen project, which is, again, something that I didn't have very much background for, but basically, as reading this paper, got a nice little introduction to it. It's searching for technosignatures, and it's searching at radio and optical wavelengths. This particular paper seems to have an advantage for having quite a wide range of frequencies that they're looking for these technosignatures for. They then give a sort of another kind of brief introduction to why exoplanets are a good target. I think the first point that they make that, again, goes without saying is that life, as far as we know, occurs on planets. And that's one good reason to look. But we also know that planets orbit planets are at least thought to be relatively common in the galaxy. So, in principle, you could look at just about any star and there should be at least one planet around it. But they point out that transiting planets have a particular advantage, which is why following up, say, TESS searches for TOIs, these TESS objects of interest that have transiting planets, is a particularly fruitful or likely to be fruitful way of searching for technosignatures. And as they sort of point out here, let's see, where exactly do they point it out? So they talk about how we've selected 28 TESS targets, and I'll jump into this figure here in just a second. But from what I was just saying here is that interesting because they have a unique relative geometry that the transiting planet implies. So basically Earth is necessarily in their ecliptic, so they're more likely to actually see us. Also, a higher likelihood of observing intentional and unintentional technosignatures. And then, of course, yeah, they may preferentially send beacons along their ecliptic because they know that they're visible from transiting planets in their ecliptic. So there's a few reasons why we'd actually want to do this on transiting exoplanets and not just any old planet. So just scrolling back a little bit here, we basically chose 28 targets, TOIs, and this figure here, figure 1, points out exactly where they stand in the sky. Now this is, SETI and Breakthrough Listen seem to operate largely in the Northern Hemisphere. So and at least the telescopes they use in this analysis are Northern Hemisphere telescopes, which is exactly why you see these TIC objects listed in blue, but the actual Breakthrough Listen objects are obviously concentrated in this Northern Hemisphere region. Now they're going to also be doing this in a few different frequency bands, these L, S, C, and X bands. Now, again, this is something I'm a little less familiar with, but basically we can kind of see from a later figure, which I'm just going to scroll to really quick. We can see there's an L band frequency density, S band frequency density, C band, and X band, the 4 bands they look at in this paper. And you can actually see on the x-axis what their frequency ranges are. So, this is 1,000 to 1,900, 1,800 to 2,600, and so on. I'm not going to run through it all, but you get an idea of that these are just different frequencies of types of emissions. So scrolling back up to where we were really quickly. So sorry, moving forward in this paper a little bit, they talk about the observations, the telescopes that we use, GBT, and then I believe APF is also used, but maybe not in this one actually. But GBT is the one they talk about quite a lot. And then they go into the analysis section, and I think whoever was giving the talk on the papers typically, right, just points out that the analysis section is one that I delve a little less into, unless I'm, oftentimes people will skip the section when they're just giving kind of a read through of the paper because it's a little specific and technical. So I kind of just moved forward. I mean, I gave it a read, but this is talking quite a lot about the kind of moving of their data storage to a new cloud platform. What I found the next most significant part of this paper to be is these definitions, which on my first read were actually a little hard to understand, but I've kind of broken down and taken notes. So they define these 3 things, which are these events. I have it written here. So they have hits, events, and then potential candidates. And they define them all in specific spots. So where do they talk about? Yeah. So hits are defined up here. And basically these are a signal on the telescope where there's a signal to noise ratio of larger than 10. Just any drifting signal with a signal to noise larger than 10 is what we're going to call a hit in this paper. But then eventually we defined this event, which is basically a number of hits that is present on all on and off observations. So basically what happens is that when we're observing a target, we have 3 on observations and 3 off observations. And if we see the hit in all the on observations and we don't see it in the off observations, then we're going to call that an event. Oh, I'm sorry, actually, I misquoted that. If the hits are present on all on observations, it's an event. If we then don't have these hits on the off observations, then it is a potential candidate. And they have a little table here that talks about these sorts of things and breaks them down by band. This is table 2. So, in the L band, we got 76 hits, 80 events, 97 candidates, that sort of thing. This isn't a summary of the entire paper, but basically we'll get to that in just a little bit. But exactly, I've highlighted this here, and they basically define what these on and these off observations are, and they have these equations that also describe how these are done. So basically kind of moving forward to how the data ended up getting distributed, it seems like the L band is kind of the one that had the most successful results much of the time, and I'll move down to the figure in just a moment. But as they kind of talk about, we have the largest share of hits. It also has the largest share of events. And we can actually even see what our candidates look like when we move down to figure 2. Yeah. So this is 4 rows, right? As we looked at this a little bit earlier. We have these hits and these candidates in blue and orange, and we can kind of see as the band breaks down, we can see that L has definitely a large proportion of these potential candidates, while the later like say, for example, the X band, I believe, ends up not having any potential candidates, unfortunately. So to just kind of, step back and remind of what these candidates are, they are basically signals that are identified as possibly technosignatures. In principle, they could come from some sort of alien life, and they start to talk a little bit about this later and why that's actually not the case for this paper, most likely. So moving on to, I think, the next thing that I think is important to talk about. They then, once they have all of these events that they've defined, they define them into bins. So we kind of make these histograms, 125 kilohertz frequencies. And they have a little bit of a breakdown here of how many they were. But for example, the L band was defined into 135 different bins. So it's a histogram with 135 different bins of frequency space with these different signals. And we, kind of talk about what these sources are doing, define single sources of interference or technosignature as event groups whose events demonstrate uniformity in frequency, SN, and drift rate. And again, we kind of have some definitions of how these things are done. And they have a sample of a plot in Appendix D that I'll take a look at in just a little bit. But basically what they also do, and this takes me back to figure 3 over here, we see the results from this particular survey is basically putting an upper limit on how likely these technosignature events are happening in systems that we've looked at. And so in this case, they put our limit of 12.72%. And as they define right here, this basically means that fewer than 12.72% of the observed stars have putative transmitters operating in this range. So again, looked at a wide range of stars, in this case, transiting planets. And we can rule out that fewer than 12.72% of them seem to be having these sorts of signatures. And it turns out that, yeah, these non-RFI results were basically, we didn't detect any of them. And what that means is that once we've found our potential candidates, we look at them and we look at them for normal things that will emit radio frequencies in these ranges. And we found that none of them were not explainable by normal physical processes of radio frequency creation. Yeah, I mean, kind of just wrapping up this paper's discussion, it provides similar constraints to previous studies, but over a much wider range of frequencies, which is one of the advantages of this one. We looked at a ton because, of course, aliens could be having technosignatures in any number of possible frequencies. And, unfortunately, no signals were found. Probably be making headlines if they were, so that's maybe not super surprising. But we are able to rule them out, at least in fewer than 12% cases in this particular frequency band. Yes, so apologies if that was kind of a lightning run through of this paper. I encourage you to look at the appendix stuff. I won't go into too much detail, but they have a few kind of interesting pieces of information here about basically data for particular targets and kind of how we're able to actually attribute some of this power to normal radio frequency sources. Yeah.
Thanks, Corey. That was great. For those of you who are still learning to read papers, this is kind of a new one because there's lots of radio astronomy jargon in there. Just remember that the more papers you read, the easier it is to understand all the details. And you read one paper and things kind of make 20% sense, and then you read a couple more, and then pretty soon 20%, you're gonna understand everything. And so it's not unusual to read papers at first, and they're challenging to understand in detail. But if you stick with it and ask questions, then you'll pick up things sooner than later. Cool. Well, that was great, Corey. And then next week, speaking of SETI, we're going to have a guest host, Vishal Gajar of Breakthrough Listens, going to give a short introduction to SETI. And so if you have questions that come from this paper, you can ask him next week. All right. And so before we conclude, we do have time for a mentor profile from Alex. Alex, you ready to do that?
Yeah, I can go ahead and start off. So,
Go
hi
ahead.
everybody. My name is Alex Polanski. I guess now I'm a third-year grad student at the University of Kansas. And I just thought I'd take, about 4 minutes to sort of tell you where I come from and how I got here. So I grew up in Los Angeles, California. Growing up, I was definitely not a math and science person. In fact, I think I had to retake geometry twice in high school. And by the time I got to senior year, while everybody else that I knew was taking AP Calc, I was still sort of struggling through pre-calc. And I think senior year of high school was the first time I ever got an A in any one of my classes. So I was certainly not the what you would call the education-oriented type. But that sort of all changed my senior year of high school when I saw Carl Sagan's Cosmos, or the OG Cosmos series that has now been revamped by Neil deGrasse Tyson. And after seeing that, I just totally fell in love. And I remember distinctly telling my parents, like, hey, I know I haven't really been good at math or science, but I think I'm going to go to school and become an astrophysicist because that sounds really fun. And the next day, my mom got home from the library and just dropped this stack of textbooks on my desk saying, you're not very good at math. If you're going to be a physicist, you better start reading. And after that, it sort of was history from there. I didn't really end up applying to college right out of high school. I didn't really think I would get in anywhere. So I ended up going to a community college. And for anyone who doesn't know what a community college is, that is just a sort of a 2-year institution. You can't get a bachelor's degree, but it's a lot cheaper than a 4-year institution, and you can transfer to another one after a few years. So I went to community college, and I was blessed to have some of the best physics and astronomy professors that I've ever had in my life. And my community college was really special in that one of our professors built a observatory on top of our math department, and one of our labs involved going up on the math department roof once a week at night and taking images of the moon, or Jupiter, or the Ring Nebula, and that just solidified my love of observing in general. And so after 3 years of community college, I decided I needed to transfer. So I decided to go to the University of California, Santa Barbara. And I spent 2 years there. And my research project there was with Philip Lubin. Funny enough, it was also a SETI project, like we've been talking today. My project involved looking for directed energy signals from extraterrestrial civilizations in far-off galaxies. So I did that for about a year. And after that, I didn't really know what I was going to do. I didn't really apply to grad school. I decided to apply to a bridge program because I didn't feel like 2 years of, or really just 1 year of research prepared me enough for actually applying to grad school. So I decided to apply to a bridge program. And by some freak chance, the University of Kansas got my application and decided, hey, like, this kid might actually be good enough for a graduate program. So they offered me graduate admission. I decided to go pretty much on a whim. I had never even set foot in the state of Kansas, and when they sent me my acceptance letter, they were like, "Okay, you have a week to decide." And I do not recommend to anyone that path of going to grad school. That is a big risk to take, but luckily for me, it paid off. And my advisor is now Ian Crossfield. I pretty much went to KU with the sole intent of working with him, and thank God I was able to, because if I didn't really know what else I would do. But now, 3 years later, I have the absolute privilege of observing on some of the biggest telescopes in the world, including the Keck telescopes, along with a few people on this call. And it's just really interesting for me to reflect on where I started in my graduate career and where I am now. So my sort of big piece of advice to everyone on this call is that it is really easy to sort of look at your life and think that the path that I'm taking is not the same path as everybody else is going down. But there's no one true path to a PhD or one true path to anything in life. And as long as you're, enjoying what you're doing, you'll get to where you need to be. So don't feel like you need to take the path most traveled by everybody else. Just make your own path and you'll get there eventually. So yeah, I hope that was helpful to somebody.
Well, it's helpful to me. Thanks, Alex. I really appreciate hearing that story. And to emphasize what Alex finished on, that there is no typical path. People, even on this call, you can see what a wide variety of experience everyone has and how they got there among all the different paths. And so keep that in mind for yourself. remember that it does take a lot of hard work, no matter what path you take. And yeah, good luck on all of your individual journeys. So is there one more mentor profile today?
Yeah.
Priya, take it away.
Hi everyone, I'm Priya, and my story I think is a little different from the ones the others said, though I was very happy to see what Alex spoke about, that it was even Cosmos, Carl Sagan's Cosmos, which got me hooked on to astronomy when I was in school, and that's when the show was aired on TV in India. I am from India, from the city of Bombay. And that's when I was hooked on to it. I was sure that this is exactly what I want to do. And we had a lot of amateur groups where we could go out observing in the nights. And there used to often be a lot of lectures in the city, by various astronomers in the country who would visit and who would visit from outside in the planetarium. And I started working in the planetarium like what was called a student scientist or a student guide. So what we were supposed to do is that before the planetarium show, you would explain a little bit of basic astronomy to people, because they had a whole set of models, and you could use the models to explain things to people. Now what happened is, so like I said, I was totally hooked on, and at that stage, a lot of my friends and everybody was heading to the US, because that seemed the obvious path to take. But I decided that I do not want to take the obvious path. And I don't know how many of you all were exposed to Russian books on maths and science and astronomy. And they were very easily available, affordable books in India at that time. And I used to read them. And that's when I discovered that it was probable to go to Russia for an astronomy program. Now in India, at the undergrad level, you could not be taking astronomy. But I knew that if I go to Russia, then I could actually do it at the undergrad, from the undergrad level. I did not need to wait for grad school to start astronomy, because I was in a big hurry to start it. And so I actually went to Moscow State University, where I did, they actually had an integrated master's program, which is undergrad and master's put together. So it's not exactly like grad school is in the US. This is undergrad and master's, so pre-PhD types. But it was a 7-year program. The only problem with the program is that you had to do it in Russian. So it was a government scholarship. You were totally paid for by the government, but the only condition was you had to do it in Russian. So in my class, I was the only foreigner in the class. And it was a little tough, because in Russia, all the exams are vivas. They are only oral exams. There are no Russian, there are no written exams. And therefore you have to be very fluent with the language so that you can answer the questions when your viva takes place. So anyway, I did my complete master's in Russia, in Moscow State University, after which I came back to India. I did my PhD in India. And then then for postdocs, I did travel abroad. I worked in France on one of the postdocs. I did visit the Center for Astrophysics in Harvard, and various other locations, even Egypt and various other countries, which I visited after my PhD as a postdoc or as a faculty member in collaborations. But I always remember the important role played by outreach and educationists in, the setting up of my career. And that's why now, when I'm already a faculty member in a university, I spend a lot of time also on education as well as outreach programs, not only for school children, but also for undergrads and postgraduates in this country, because a lot of them, do not have exposure to astronomy in the sense of actually doing student projects or, doing something in research. So especially in the COVID times, and even before that, we've been actively doing programs on students doing research programs. So I've been conducting some projects since last year with the International Astronomical Union Office for Astronomy for Development, where we are actually doing projects with undergrad and grad students on research. And the speakers are from all over the world who actually have been talking, mentoring, and helping. I've been also mentoring projects, and that's what I've been busy with. So thanks. Howard, I'm done.
Thank you so much, Priya. That was great. And again, what an unusual path to astronomy, going to Russia. That's crazy. And you made it. You're a professor. That's so cool.
I thought that would be different because everybody was running to the US. I said that go the other direction.
I think it's wonderful. All right, I'm just gonna wrap the class up here with a little preview of next week. So we only have a couple weeks left. Coming up next week is the special guest lecture from Vishal Gajar. We'll do a little intro into the final projects, and then there's one more paper that I'll send the link around to. It's a direct imaging paper. So we've talked about radial velocities, we've talked about life in the universe, we've talked about transiting planets, and so this will be a direct imaging paper, which will sort of complete our the three primary methods for detecting exoplanets. So stay tuned for that link. Should be live on the GitHub page. Do work through your radial velocity tutorials, and there'll be a solution posted next week, and there's help online in the meantime. Thank you all for your contributions today, and thanks all for coming. We'll see you all next week.